No. I'm going to start.
Oh, okay. Do they make it?
You hear it?
Yep.
Okay. Let's go to the pocket. Okay.
There we go.
Awesome.
Okay. Good evening, everybody. Can anyone hear me? God. Good evening. My name is Lee. I'm going to be the host this evening. But as usual, it's the community that makes these events. So please keep your questions free-flowing and volunteer your experiences for the benefit of the crowd. Show of hands for anybody, is this their first TensorFlow meetup? Okay, great. Well, this is a very open and supporting community. I hope you'll find that this evening. So I encourage you to support our speakers, and they have happily agreed to share their work, both for broadcast on the web and for dissemination of their slides. So, a little bit then about this evening. Aside from the Grim Reaper's overactive side amongst the celebrity population this year, there have been some quantum leap in the field of machine learning as well. Unbelievably, TensorFlow celebrated its first year. Seemed almost impossible that that's become the most popular machine learning project on GitHub in that short time. So we're very pleased to have so many people here supporting the community. And I encourage you to take a look at some of the document pages as well. I want to do a bit of session on thanks. First of all, our thanks to Alteros, who are not here on the slide deck. Thank you, Alteros, who are our co-hosts, and to Google for the supply of pizza and beer today, so thank you to those guys, and to Rise London, our venue hosts. Actually, I'm just going to ask Stefania, who represents Rise, to just give a few words to describe the work that they do.
Thank you very much, Lee, and thank you everybody for coming back and coming as well for the first time. Here we are, Rise London, the home of fintech, and not too much. So we are happy to be the home of the Barclays Accelerator program here, which Seldon is part of, really. So this is a program designed for a fintech startup that basically gets a support to bring their service or their product into the market. It's a 13 weeks program. The next course will start on the 23rd of January 2017. And Seldon is just one of the best startup that ever taken part at this project. Also, we have an amazing co-working space at this event space, which is completely free of charge for any fintech event. We actually moving fairly soon to a new location. We will bring exactly the same structure as we have it here in Rise, Whitechapel. The new location is going to be in Shoreditch, so a very fun and nice area. If in the audience there is an event organizer interested in hosting their event at Rise, please let us know. I have on my business card a little bit all around outside, so feel free to take it and let me know about your future project. And then we will have also a co-working space with many many possibilities. Membership as clubs or hot desking or private office or set desk. So there are lots of opportunities. I hope you decided to sign up to the London Rise letter, because this could be a way to let you know about our news and what's going on, about the new site and everything. A little more information about this site actually for tonight. So there are no fire tests in plan. So if you hear a fire alarm, please, those two exits are the ones you should take. Please ignore that sign over there. Toilets and emergency exits are not there anymore. Equally toilets. So outside here, straight ahead in front of me, through the glass door. Say that, I pass back to Lee. I wish all of you a very pleasant and productive time at Rice. Thank you.
Thank you, Stefania. So, wonderful hosts. Just quickly then, looking forward to next year as we bring the year to a close. The 2017 calendar, I've been asked to point out there is a TensorFlow Developers Summit on February 15th. For those of us who don't have a ticket to Mountain View, they will be streaming that event live. So anyway, enough waffle from us. You know who we are, Seldon. We're Machine Intelligence for Enterprise. I encourage you to take a look at our docs page and explore our demo using TensorFlow that we explored last time. But this evening in this session, I want to start off with our first speaker of the evening, Arseni, who is going to join us from Gluru. No.
Come out. Is this one? Sorry.
Hello. Apparently the thing is picking up my heartbeat. And I'm really happy here. So we'll go with that one. So just like short introduction slides, my name is Arseni Yusimovic. Here are some links you might find useful. The first one is the repo for the presentation. So feel free to check out now or later when it is for any question required. If you have any questions about Gluru, first email, personal one second. The slide I'm not allowed to use Gluru. We are smart to the list, so we integrate with your channels and we help you identify tasks and suggest the right answers when you need it. Website, we have applications for the web. We are in iOS beta soon. We are hiring, so if you're smart R&D scientist or a core engineer, just drop a message. We'll go from there. We love Python, Go, TensorFlow, and really cool to learn something. Next, about the TensorFlow, what I will be talking today. As an NLP specialist, I quite often struggle with really scaffolded solution to try really simple approaches to the task I'm trying to solve. And what I want to do with the talk, with the rep, is to gather all these simple models, ranging from the dumbest one to the ones which are proven to be very okay for text processing, and gather them in one space and compare the performance. So what I chosen as an object is social media. A couple of facts, and you'll see why it's important. About a third of Earth's population uses social media, and I will talk it through. So 78% of US population is on social media, Facebook is about 1.7 billion rate, and for example, Twitter reported 6,000 tweets per second, and if we go to the dream events of US election, that very day it took about 75 million tweets alone. Why it's very, very important, social media is a place where people used to express their opinion, but now, and it's doubtful, it might be, and I might sound stupid, like conspiracy theory kind of guy, but it's used to amend people's opinion, and as data scientists, as people knowing how to use data, we don't only have the way and tools to look through data, but we have like some kind of moral right, not only being startups, but try to understand data and explain it to those who don't see. So that's why I chosen the task of multi-class classification. And of course, most of you have heard about sentiment analysis, but any kind of binary or ternary or any classification can be applied to anything. So you may take the supporters of certain campaigns in a certain country to like tweet certain aggregation of countries and use that as your data set for racist, non-racist persons. Or you can look into the elections and you can see who supports who. That data set is not available, so to mimic what I wanted to show, I used the Sentiment 140 data set from Stanford, and for simplicity, for you to reproduce results where if you wouldn't do the charts, I took the first 40,000 examples as an input for the models. What I will cover today is 4 models, ranging from simple to the most prominent one. First is logistic regression, then feed-forward network, and convolutional network, and the latest I found is character level CNN. So, first, logistic regression, like really simplest approach. How would you analyze any kind of text? Wow, nobody was hearing me all the time. When you look at the text, how do you actually analyze it? You take it, you just dissect it word by word, and that's our input. What we do, we just assign weights for every word we've seen, and we output that as softmax layers to basically get the probabilities of every class. How does that actually perform? Seems like the approach is really simple. That's the charts from TensorFlow when it's training, awesome tool. We reach the accuracy on the dev data set of about, let's see, 83% accuracy. Yeah, so really respectable numbers. Usually people would like to get way beyond that number, and they will try to apply next things. Next things comes to mind using the same input, so the same layer of words. We would like to let neural network to optimize over some patterns we might not see in just words. So we had a hidden layer. I used absolutely random division by 2 to simplify the task of classification. The output layer is just the same, the probabilistic layer of softmax. We may add biases on every step, and surprisingly, if you take that, you get the lower precision, lower accuracy, and the model does not perform at all good while it reports itself training. So as soon as you add any hidden layers, you start overfitting quite quickly. But that approach is very simple, and nobody uses words. You might sound very simple if you approach that as a problem. What is hyping right now, what has actually proven itself quite useful, the convolutional neural networks, which go from the object recognition, and basically who is not familiar with the concept. So I go into details for now. Yeah, all good? Cool. So for network, we use the input layer of words. We assign any kind of embedding layer, and we transform words into really unreadable vector. And we do all the convolutions on that very input. And then output it as a flat layer, and again, probabilities. And the results we get are at, again, 76%. So we basically don't get any improvement if you use heavy computations and that kind of stuff, and the network becomes overfitting again very, very, very quickly. The last approach he wanted to cover, and that's actually a very nice advance in the field, the character level network. You can read the original paper on the convolutional neural networks for text classification. Like one of the authors, everybody I think heard of is Jan LeCun from Facebook. Yeah, so input for the network is the alphabet of your language, of your task. So you try to make the convolutions on the level of letters, and in that way you don't really look into the meaning of words, which you may extract from like word-to-vec model as the previous one, but you try to learn the language. The authors in the paper claim to achieve quite high level of accuracy, which is comparable with state-of-the-art problems, state-of-the-art solutions, sorry. Well, my attempts to code it first melted our server. I was told not to do it, so I decreased the dataset quite heavily, and what I got is just that. So the main assumption I made from that, you have to be learning on a really large data set to use any kind of convolutions. Basically, if you take first 80K random sentences, you just don't gather enough knowledge about the language itself, so you lose all the power of convolutions. And that's kind of doesn't lead anywhere but melted. So, oops. So if we take the joint results, that's how it looks like, and what I wanted everybody to take out of that is never discard the simplest solution, because sometimes it's a good baseline, and from the chart you can see like the blue line represents the first model logistic regression, and it achieved the same accuracy as the convolutional neural network works, and it achieved a bit slower, but well, efficiency is the same, and why use the heavy computations if you cannot? That's kind of goes to the conclusions of the talk, and I'm probably quite fast. So simple solutions is usually a very effective baseline, and if you can understand what's happening, it helps you to understand what will be happening in more complex networks, and you will have the ability to answer why your hard network isn't working. Other advances, so like improvements in neural networks, they provide usually better quality, but in many cases not very decisive until you spend like ages, months into like wiring all the parameters and trying to find the best network topology. Modern advances provide us language agnostic text analysis, given we have the access to really big data. If you work in small data sets, just don't really try to use it. You won't succeed usually. We will be making the model less interpretable if we use modern advances. And yeah, it's always good to use a new network to get your new laptop or new powerful server. And the last one, it's kind of like Jackie Chan bloopers. You should be very careful when you write code from the scratch, because at one point I mixed up plus equals with equals, and I solved the task of sentiment analysis by 99.9%. And I was super happy because there is like semi-val task, which has the sentiment analysis. And I thought I will be going there like a boss. Just, guys, 80% is not enough. But yeah, really be very, very careful with that. Questions, welcome, because I think I was quite quick with the task.
Hi, I'm Chris, work for Ocado, which I guess everybody knows here. Did you play around with your network hyperparameters and say I'm only a beginner in neural networks, but I would probably, if it's overfitting, maybe try some dropout layer, something like that. Any of that?
Yeah, it actually is integrated into the network, and it doesn't help with the default parameters. For the network on the character level, I used the solution provided in the original article. For the text-based one, I used like fair random dice roll. So it's not like I'm not trying to fix it, but it doesn't. And it happens in small data sets as far as I've seen from the experience. So the smaller task, like if we go to the previous slide, it's not only a really bad like way of coding, but it shows you that the logistic regression model, which is the orange line, even given the full knowledge of data set, isn't able to memorize it. So like it gives mistakes by 80%, but the convolution it learns it like completely. So it just tends to be overfitted.
Hi, my name is Robin. I work for IHS Market, 15 billion listed on the NASDAQ, I think. I'm looking to use this to analyze and verify all services, but I'm still learning. And the question is, you said that you needed very large data sets and that you weren't allowed to take the service down by asking it to do too much number crunching. But the first data set we saw, it was, you called it 140, and I can't remember where it was from. It was from the first data set was something 140. Have I got that wrong?
It's sentiment. It's the name of data set, sentiment 140.
Yeah.
It's like a couple of billions of tweets.
Okay, yeah, I didn't.
But I took the
very
very subset.
tweets.
Yeah.
And you said that one was not big enough, or that was too big for you
I
to
didn't
use?
try to actually. I didn't try to use all, but if you like, usually you don't have big data set. So if you're talking about billions of examples, it's really a big company which gathered the data quite for a long time. But if you start at the field, or you are stuck with either whatever you got, like annotated yourselves, which is like a couple of hundred sentences, and you are already tired, or you got some crowdsourcing, again, it's like money waste, and the quality is not good. Again, the size is small. So when you start small, we'll see the results like that.
Yeah, overfitting.
Yeah, and overfitting plus the like really low language level models wouldn't work.
But it's with linguistics, there's quite a lot of structure in sentences, and than let's say white noise or whatever. So so how my question was how big in like after your research now, how big for understanding linguistics should the data set be?
As big as language itself. Basically, if you take the difference between like third model, convolutional, and the character-based, the difference is the convolutional net. It may use the word embeddings pre-trained in any data set. So basically, we'll take whatever data source we have in English and learn that, and we'll find the knowledge of English based on that. When you try to learn the same from characters, you are stuck with quite lower size of language. And if you look into tweets, you have even less, because the language is way simplified. So based on task, at least a couple of thousand sentences for binary is fine. But I used the formula for the test data set. If you have a test data set of 100 examples, one mistake is your 1% of accuracy. Yeah. So if you want to have some rough precision of measurement of at least 0.1%, you have to have at least some inside the size of the data set, and so on. That kind of answers the question. Yeah,
Okay, I'm going to ask our second speaker of the evening, Oliver, to step up and give his presentation whilst I tee that up. We'll take some questions for both of our speakers this evening at the end of the session as well. So if there's anything that you wanted to address to us, save that up for at the end of the session.
Hello everyone, my name is Oliver Gindele and I'm a data scientist at Datatonic, and tonight I'm going to talk a bit about predicting traffic and congestion in London and a bit about myself. All right. I have a background in computational physics and high performance computing. Now I'm a data scientist at Datatonic, and at Datatonic we're a small team of machine learning and data science experts, and we try to deliver analytic solutions to bring fast and actionable insight to our clients. So the whole story of this little project we did on traffic modeling actually started with a hackathon at TensorFlow London, and I'm sure you all know TfL, probably used one of their services to get here. And you probably all are aware that they're dealing with a lot of congestion, be it on the tube network or on their roads. So they tried to tackle this by releasing some data sets. And through the hackathon, we got access to one of their data sets containing sensor data from their road network. So you might have seen those sensors. They're usually on junctions, they're those induction loops, square shaped on the ground. Nowadays, they're little boxes, little cans on the ground. And what they do is they just measure whether there's a car above them or not. That's all they do, and they usually use to regulate the nearby traffic lights. So the whole data set was 5 terabytes of data, 100 billion rows, and it originated from around 40,000 sensors all over Greater London. And with that same data set at hand, we thought, well, isn't there a way we can now have a look at the state of the traffic right now and forecast it in the future? Because that would help TfL to manage road traffic, to avoid gridlocks, kind of foresee what's going to happen by just looking at what's the case right now. And the kind of overview of this whole architecture we built, and it's also the outline of the talk. I'll use my hands. So we start with the data right from TfL, the 5 terabytes. So we have to do some pre-processing because that's raw sensor data. And I know you all want to know about the TensorFlow model, but I'm going to talk about the processing and a bit about feature engineering, because I want to give kind of the whole process and the whole data science perspective on this. And from the TensorFlow model, then we show and see how we can forecast congestion in the future. So the pre-processing, the hard bit first. Data we received kind of look like this. Probably can't see it at the back, but it's just rows with 4 bits, and they signify whether there's a car above or not. And they have some annotation, timestamps, type of junction, geolocation, and so on. So in the pre-processing, what we want is we want to get this bit stream in 5-minute windows, where we just have zeros if there's no car, and we have a 1 or a chunk of 1s when there's a car passing. And we can do a little bit more math on this, but I'll talk about this in a second. The way we did this is we used Apache Beam, which is a distributed computing engine, if you don't know. You're probably familiar with Spark. It's kind of similar, but it's more meant for ETL processes, something you pass through once. And the nice thing about it is that you can use pretty much the same code whether you deploy something in batch or in stream. So you change 1 or 2 lines, and you can do this whole thing we did in batch in real life and do some real-time visualization of the traffic data, for example. That's quite powerful. On the right, you see the pipeline as we executed this Apache Beam job on Google Dataflow. That's just the execution engine. And we run this overnight on 100 machines. And yeah, took maybe 12 hours or so. And what we did with this is we actually engineered some traffic data. So you saw the bit stream. And from this bit stream, we can calculate 2 more measures that are quite important and quite often used in traffic theory. One of them is flow, and that just tells you how many cars pass. So think of a bit stream again. It's literally a chunk of 1s passing through your 5-minute time window. We got this for every sensor. And then there's density, and that shows you how much a sensor is occupied, so how many 1s are there compared to the all your bits. So this is gone now. All right. And I full screen this. So flow and density, quite important parameters, but neither of them gives us a feeling about congestion. They're all good to analyze traffic, but if we want to know how much congestion there is at a given time, we need something more descriptive. We played around with flow and density, but the issue is if flow is low, if there are not many cars passing, it doesn't mean there's congestion because the flow can be low at low density, you see in this diagram, or the flow can be low at very high density. So neither of those, the cause is just different times during the day. So you see it kind of evolves during the day as traffic evolves. But we want to come up with something beyond that, and we could calculate speed. So there is a measure of the average kind of speed per sensor of the cars passing that, and that's just flow divided by density. That's not quite enough as well, because the speed might be different from road to road, so we use the relative speed. Missing, it's unfortunate. But you can divide the speed by the maximum speed, which you probably achieve somewhere at night, and then you get a relative speed. And the nice characteristic of that is it's 0 if there's congestion, and it's 1 if the road's free. So now we finally have a measure that displays congestion in a simple way. You can also visualize this potentially in real time. And it's something we can finally learn a neural network. So finally we move to TensorFlow. And what's better to kind of look at this series we've got than a recurrent neural network that has this sequential structure. Because now we have for each sensor, we have a time series of these congestion values. And those are at a 5-minute level. And that's happening, that's what we got for all the sensors in London. And the pre-processing, not just did it map it to those values, we also cut down the data size quite a lot from the 5 terabytes to something that's less than a gigabyte now. So we can deal with that in TensorFlow, and we use a recurrent neural network, which usually is pictured like this. We have this loop of the hidden unit, we have an input and output, where you can unfold this. We have the sequential steps where you get information from the past and information at current values. And it's nice because this has kind of a memory, and it's used in all sorts of neural language processing and language modeling, but of course also in time series. So although in theory it works quite well, in practice, normal recurrent neural networks, they tend to forget what's happening past, way at the past. And that's the issue of the lack of long-term dependencies. And that's generally related to the vanishing gradients when you train those models. Because now we have a little bit different picture, but the same structure of hidden units, input, output. But quite often they struggle to learn dependencies that are very far back. So this neuron won't really know what's happening here. And that's because on training, through the back propagation, when you train the layers, you have the gradients that become very small as a result of the sigmoid activations you usually use in those units. So the sigmoid will kind of level out at 1 and at the low level, and that means the gradients are very small. Now, do the back propagation, not just within each current state, but also back through time, you'll multiply very little values, and they will just vanish exponentially. So what you end up is with a neural network where it might happen that if those neurons are saturated in between, the past state can't really contribute to the future, and you're stuck with something that can't learn the past very well. So that was a recognized problem, and already 20 years ago, people developed something called the short-term memory neural network, short LSTM. Most of you are familiar with this. And the idea behind this was to kind of introduce an additional state, a memory, that runs through all your hidden units and provides some persistence on the information. And if you just look at the similar structure of the RNN again, and we have a close look at one of the units, we see that we have this cell state, and now we have a few different gates that kind of interact with this. So the first gate in an LSTM will be this one here, and that's a forget gate. It decides how much of the past do we actually feed into the current state, or the current cell state. Then we have those two activations here, sigmoid and the hyperbolic function, which also add to the cell state, but they define how much of the current state we're going to feed in. Those are called, that's called the input gate layer. And then there's the last bit over here, the third gate, which is the output gate, which decides how much of the information you pass on to the future. So with those three gates, it's what's called an LSTM, but they're more recent implementations. For example, the GRU, which only has 2 gates, and you can replace those 2 gates by just one, or the peephole connections, where you talk much more back and forth with this cell state, or their more recent advantages like grid LSTMs, or bringing attention also into the space of recurrent neural networks. So with that tool to kind of model sequences very well, we want to go to TensorFlow and implement this, and the nice thing is it's already there, right? So even the very advanced models like grid or attention, you already find a layer or wrapper in TensorFlow. It might not be documented, but it's probably there. So you can go easily beyond LSTM as well. But we choose to stick with the LSTM. It's well known, it's basically the go-to recurrent neural network. It's just a bit of code to explain how we put it in. So that we do some reshaping, that the input matches the cell. Then there's the simple LSTM cell. We actually add 2 of those layers in the implementation. And it's as simple as just selecting a multi-RNN cell and stacking your layers. We add dropout. There's a wrapper function for that. And then there's the RNN.RNN function, which simply unrolls the graph in TensorFlow. So you have this kind of looped sequence, and RNN will just unfold it. And in the end, there's just a linear output activation. So one more nice thing is if you deal with sequences in TensorFlow, is you can actually process them at a time in batches. So instead of kind of chopping up everything beforehand into a sequence and labels, we can do this at runtime. And that's important because we're still having this time series of congestion values. And we want to train the network on something. So what we decided is we look 40 minutes in the past, create a sequence of that, and then assign it a label that's 40 minutes in the future, so we can predict this 40 minutes ahead. And that's just done here, where we can use a feed dict to, at training at run level, when the session is run in TensorFlow, we'll use the feed dict, and this will actually call this batch processing function, and we'll just calculate a new sequence and a new label at runtime. If your data goes very big and it doesn't fit in memory, that obviously won't work anymore. And then you maybe need to redirect it from this or look at other approaches. So now that it's easily implemented in TensorFlow, we can actually look at the results after doing some training. And the training itself was done on a reduced data set. So we didn't use all the 14,000 sensors, but 300 and 4 weeks. As I said, the sequence we generate is 40 minutes back, and we want to predict 40 minutes ahead. This kind of allows us to sample traffic state right now and to pass from the past 40 minutes, and then show what it's looking like, what it looks like in the future. We used Adam, 128 hidden units. We did a little bit of hyperparameter tuning, but there was only a small proof of concept. That's why we reduced the data set, and we didn't scan for everything. The loss function was root mean squared error. We had early stopping on this. We saw the dropout layer, and we actually only trained this locally. I said less than a gigabyte data. 2-core machine ran for 2 hours. So what do the results look like? Those are now the actual spots of the sensors where you find them in West London. So the 300s I was just talking about. And we select like a few to display here. And that's what you see down here, where you have the green curve, which is the predicted values, and the gray curve underlying is the actual. And what you see is actually on these few sensors, you have the dip at morning peak hour. It kind of dips a little bit in the afternoon as well, so it finds rush hour, but it also follows it generally quite nicely. If you look at maybe all sensors together, you can compare at the top the predicted values. Actual is in the middle, and the difference is plotted at the bottom. So now you see the congestion values I was talking about. So red is pretty much 0, no part. Pure congestion. And everything's flowing. And if you look at the difference, you find that mostly it agrees very well. So this is taken at 5 in the afternoon, probably a very disrupted traffic state, lots of congestion as you see here, but the model does very well. There's a few sensors, they act up, they don't agree, so this here is the error. Green is good, red has a large error, but generally, training it only on this reduced small data set, we get quite some good accuracy and quite some good agreement with the real numbers. We can also look at all the sensors next to each other. I mean, this is only a subset of maybe 20. But you see that not only do we have the time series during the day, the LSTM also distinguishes each sensor nicely. And we don't have a single time series, we have 300 time series. And the LSTM will pick up correlations between them. And we'll find that at some point, this sensor will dip largely in the morning, given some values in the past, and there's an afternoon rush hour peak. But other sensors stay very flat. So the model is definitely capable of kind of picking up these differences, and it doesn't just produce something on average for the whole London road network. So with that, we probably eventually would need to go beyond the, there's another slide missing, beyond the 300 sensors we just selected, and we would want to train it on maybe all the data we have, speaking 100 times more than we actually trained it on. And in order to do that, we need to scale it up, but TensorFlow is nicely capable of doing that. So either deploy it on a large machine, deploy it on a GPU, you don't have one at home, use AWS, and recently as well Google, or you can deploy it on Cloud now, which is a Google service, integrates nicely with TensorFlow. It allows you to prototype it locally, which is deployed there, and then you can train it, distribute it over several machines, and also serve predictions from there actually. So that's a quite nice service. But just recap again, we did a lot of pre-processing, and to make this bit stream from which we calculated a few measures, which took some conscious effort about traffic, and that was then the result we fed into TensorFlow, which allowed us to get those predictions you just saw. Just to give a little bit of scope, we did this in a bit more than a week, but it actually took much more time to do the pre-processing and the feature engineering than building the model in TensorFlow. And we definitely spent much more time, much more money on the pre-processing. And this might mean that the deep learning is not the hard one, but you obviously saw we just made something work and had a proof of concept. But it also means how good TensorFlow is at getting things run very quickly. You saw the LSTM does well, but it's also already implemented. It's a few lines of code to get something like this to work. Obviously, you have to build a few things around it, but it allows you to prototype something very quickly. But then it also allows you to go beyond that and do comparisons, train it, and employ the actual state-of-the-art research on it. A nice thing to also have is these feed dictionaries, which allow for processing at runtime. And yeah, you can literally scale it, and it would be an easy exercise. Well, it would cost a bit of money, but to do it on the whole data set. Maybe the use case again to wrap up the TFL bit, traffic bit, is that now there's a way to forecast it with some good accuracy, and it can be used to avoid gridlocks. Kind of look at the traffic state now, and if there's something weird emerging, you can actually react and manage it in a fast and effective way. And you can also detect incidents very quickly, because you can make a prediction, compare it to the actual state, and if that differs, then you know there's something wrong going on. So that was pretty much it from my side. And if there are any questions, that's the time.
Zoe, how would go?
Very practical one. Have you compared the Cloud ML and AWS in terms of costs of all the TensorFlow? Yeah, it's tough sometimes.
So the thing with Cloud ML is it's still, parts of it is still in alpha, so there's online predictions, and you can't really compare the cost there. I think we did compare the TensorFlow server versus Cloud ML in terms of how many requests can it serve. And I think there wasn't a clear winner in terms of performance or pricing, but it probably, I think, in terms of pricing, what's important with Cloud ML is that you have, when you have a trained model and you just want to serve predictions. And if you do that in the long run, I think the pricing information is not there yet, because it's still alpha and it might still change. So I think you have to check the Google space in the future.
Yeah, hey, do you have any idea about any other potential use cases for, I guess, machine learning, TensorFlow type techniques that TFL are actually looking at, or you guys, Datatonic, have maybe kind of thought might be exploring with them?
So TFL is generally very good at handing out data. So if you check out the web, actually, big thanks to the guys there who gave us this data set. There's a lot there that can be done because you have bus arrivals, tube arrivals, all that. So yes, I would say there's a lot to be done. TFL, they don't do those things themselves, but they having periodic hackathons where they enable people to come up with an app. But it's very solution focused, and they obviously want to help the people. So the products generally should be something that you put at hands of the customers in London. But within that, yeah, there are lots of possibilities. For example, they're going to release some data on crowding of tubes and tube stations. And I think there will be a lot of modeling and prediction that'd be very handy for people on their daily commute.
My name is Joe. So something about regarding that hardware bit. So you mentioned that you have to train it through local machines, right? So do you have like multiple GPUs using the machines, or like you mentioned you also say that you are able to achieve like within 2 hours training time. So what kind of machine do you have? Just a random question.
So you want to know the hardware we use to train it?
Yeah.
There was just a compute instance on Google Cloud, probably same as any cloud service. So just 2 cores, so very small instance, small RAM, nothing out of the ordinary.
So it's not really something local, completely local, right? So using.
I wasn't done on a laptop. No, it was a compute instance.
Hi. Did you use a standard machine learning kind of regression algorithm before you tried TensorFlow?
No, that was what we did straight away. We did a lot of analysis and maybe on some levels some clustering to kind of see what's happening with the data, but that was more for the feature engineering. And we thought on this scale with this data, it's probably the best bet. But maybe as you showed, some simpler methods also need to be very good at.
Sorry, Peter. Are you actually going to play with it further?
That's pretty much on the TFL side now. So we've done this, and I can show all this because it's kind of open data. Well, it's not available, but it was available through the hackathon. But if they have any interest in that, yes, we'll probably take that further.
One of those things where you're ignoring the elephant in the room, where the actual location, the proximity of the sensors is another feature. Because if you pair it with sensors, like 2 sensors into 1, you could understand that as a recurring thing. But you're just looking at 1 sensor at a time.
Yes, yeah, but I mean, the LSTM will find correlations between them.
No.
But there's no
You passed more than 1 sensor in.
Yes. Yeah, that's what we did, yeah. Passed them, we trained them on all the data at the same time. Okay, in that sense, yeah, I agree. But in the recurrent architecture, all the parameters are shared, so it will. Yeah, that's probably true.
Hi, my name is Peter Kabinski. I'm just curious whether you made any data analysis of the which junctions were not very good and not very failed in your estimations, and whether there is something about topology of the junctions that were usually not well performing not well in the model. And the second question is, any of these things are reproducible or possible to reproduce?
About looking at how performant each junction of sensors, no, we didn't look at across the board. We only had this small set, and we didn't do a thorough analysis on that. And can you repeat the other question about reproducibility? Yeah. So the data is not freely available, but if you're interested and want to have a look at this, well, we wrote it up in a blog post, but the data, no, I don't think TFL will release exactly this data, but maybe there will be a time where they're going to release the road sensor data streaming way, as they do with other services, but not ever.
Any more questions?
Sorry, another question. So you also mentioned that you also did some feature engineering before you put data into TensorFlow during the deep learning. And like the deep learning is kind of like we can escape those feature engineering, so we can just directly plug data into the model. So any comment on that? So what's the typical feature engineering you do on this type of some project?
So in this case, what I meant by feature engineering was going from that original raw data, or the bit stream we had, to congestion values at the 5-minute level. And I think potentially, yeah, the deep learning models will find the features themselves, but we just thought it's easier to actual congestion values than just trying to predict this bit stream. So you can go ahead and try to predicting zeros and ones, but I think you're going to have a very hard time doing that.
My name is Michael and I work for B&J. My question is, beyond TFL, traffic-related applications, do you think this approach will be useful in flood management of maybe a river system?
I mean, the approach of an LSTM is very general and will always apply to time series. So if there's some data in the space where you have a time series of whatever, levels of water levels of rivers or things like that, it needs to be something, a flow of river, yeah? Quite likely, if it's a sequential data set or a time series, you'll probably always get some early good results with similar architecture like that, but it depends on the problem in itself.
Do we have any more questions for Oliver? No? Just remains for me to thank our speakers. And to thank you, our community and audience team. This is the last TensorFlow event of the year, I believe, and probably one of the last events at the venue. So I invite you to have a beer with a song and a pizza. Thanks very much, guys. Hopefully, happy Christmas. See you next year.